Righty. So let's see, before we actually plunge into notes 9, I thought it might be helpful to go over one more blast from the past. So let's pull up blast number 2. Okay, now this one happens to come to us from exam 1 exactly 1 year ago. Okay, let's go ahead and read it. It's kind of lengthy here. A voltage source is applied at the left end of a transmission line as shown below. Okay, so here's a plot of the generator function. Okay, it's kind of like a triangle function, but with the top chopped off. Okay, let's see. The transmission line here meets a second transmission line. So this is line 1, this is line 2. Okay, which is terminated by a load. Okay, looks like it got chopped off though. Sorry about that. But it's supposed to say RL equals 50 ohms. Sorry about that. I'll correct that later. The pulse peak, V0, is 8 volts, and the width of the pulse is 3 nanoseconds. So 8 volts here and 3 nanoseconds. Now notice these breakpoints here are 1/3 of the way down and 2/3 of the way down. And the entire width is given to us as 3 nanoseconds. So that means this time right here is 1 nanosecond, this time is 1 nanosecond, and then this time is 1 nanosecond, okay? All right. Plot the voltage V of t measured by an oscilloscope that is connected to the first left line at a point halfway down, halfway between the generator and the fault. So right here, here's the fault. The fault is modeled by a parallel 10 ohm resistor. Some kind of break on the line or something, but it's being modeled as a fault on the line by a resistor here. All right, and let's see, plot to a time of 10 nanoseconds. Use the graph on the next page and make your plot. So in this exam, we gave the graph and you have to add your plot to it. Label all voltages on your plot, okay? Does everybody understand the question? So oscilloscope attached halfway down the first line right here. What would the oscilloscope read with this waveform applied at the generator end? And again, you have line 1, line 2, and then you have this fault here. So both lines are 50 ohms, and it's supposed to say, got chopped off, but it's supposed to say the load resistor is also 50 ohms. But then you get this parallel resistor here of 10 ohms, modeling the fault on the line. Okay. Now, the answer is on the next page, but let me maybe ask you first. Let's say you're on the line 1 here, signal's coming down here from the generator, getting ready to hit this fault resistor. What kind of resistive load do you think that incident waveform is going to see when it hits this junction, this fault here? Any guesses? Now, if that fault resistor weren't there, there would be no reflections because this is 50 ohms and this is 50 ohms, right? So what we call gamma J, the reflection coefficient at the junction, would be 50 minus 50 over 50 plus 50 be 0, of course, right? But there's this resistor right here on the line. So if you're looking from the left, in other words, you're this waveform coming down from the left, getting ready to hit the junction, what kind of a resistive value do you think you're going to see? Any guesses? Now remember, when the waveform first hits this junction, we don't care about what's going on at the load, right? No. Now the waveform would go down and bounce off the load and come back. In this case, it won't even bounce back from the load because the load is matched, right? Also 50 ohms. But even if it wasn't matched, it would take some time for the wave to come down and hit it and bounce back, right? So we're not worried about that when the waveform first hits the junction. We just want the reflection coefficient at the junction. So we need to know what is the resistance that the waveform sees as it looks into the junction, first hitting the junction. So what do you think? What do you think the resistance is going to be? You don't have to give me a numerical value, but how do we calculate it? Say again? Oh, with what? Okay, so you're right. So 50 ohms here in parallel with. Well, 10 ohms is the resistor. What's it in parallel with? Yeah, right. Very good. Very good. So now when the waveform hits this junction, if you pretend this resistor wasn't here, then this is like what we did in class with that 2-line problem, right? So when the waveform first hits the junction, the resistance it's going to see is whatever the Z0 here is. Don't worry about the load when it first hits the junction, right? It's going to be whatever this Z0 is, which happens to be 50. But this thing is then soldered here in parallel with whatever you see looking in at this junction here, looking to the right. So it's 10 and 10 in parallel with 50, which happens to come out to be 8 1/3. Everybody understand that? Okay. So now you know the answer. Here it is given away. Okay. So the gamma L, now it's kind of confusing notation because normally gamma L in the notes means the gamma off the final load, right? Because this is called the final load resistance. Kind of bad notation, but gamma L now on this slide means the gamma looking into this junction, thinking of the junction as the load on the first line. Okay. Sorry for the slight conflict in notation, but that's what gamma L means on this slide. Okay. So the gamma L is going to be this parallel resistance, 8.33 minus 50 over 8.33 plus 50. Now this 50 here is, of course, this 50, the Z0, the first line, right? So it comes out to be minus 0.71429. Okay, the generator is matched to line 1, so of course you don't have to worry about any gamma on that. And then since the Thevenin generator is 50 and the Z0, the first line is 50, the voltage divider coefficient is simply 1/2. Okay, so notice when the waveform first comes out from the generator, it gets launched on the line. Notice that the amplitude is not going to be V0, which was 8 volts, but it's going to be 1/2 of that, so it's going to be 4 volts, right? Because the A coefficient is 1/2, right? So that's what the incident wave is going to look like coming down the line. But then it hits here and bounces back. Now, the problem asks for an oscilloscope trace halfway down. Okay, the transit time on this line, actually both lines, is 4 nanoseconds. So the time going from the generator to the oscilloscope is, of course, 2 nanoseconds, right? So the incident wave is going to look like what's coming out of the generator, but with half the amplitude, that's going to be delayed by 2 nanoseconds, right? That's the incident waveform that sweeps past the oscilloscope. Now, here's that formula that we saw a second ago from the homework problem. Okay, so here's the voltage that we expect to see. A is 1/2. Okay, so it cuts it down by 1/2. And the generator is matched. We don't worry about reflections from the generator. So all these terms are gone. So the answer is found from just the incident wave and then one bounce. The wave that comes to here bounces with the gamma L that's equal to this and then sweeps past us going backwards. Once it hits a generator, it's gone, right? Okay. Now, so notice we have to put a gamma L here. Not only the 1/2, which is the A coefficient, but the gamma L, which is minus 0.71429, right? And now what's the delay going to be when it bounces back and crosses the oscilloscope? What's it going to be? Remember, this delay was 2 nanoseconds going down to the oscilloscope. Now it goes all the way down. Okay, that's 4 nanoseconds. And then it bounces back. That's this time delay. Can you tell me what that's going to be from here bouncing back to here? 2 nanoseconds again, right? So a total of 6 nanoseconds, right? 6 nanoseconds delay. Okay. So here it is. First wave is delayed by 2 nanoseconds, second by 4 and 2, so 6 nanoseconds. And then don't forget that gamma L. Okay, so does everybody understand? Now, you can, of course, multiply this out, obviously. I'll do that in the final plot. Does everybody understand that equation? Okay, so just remember the delay principle. It's pretty easy, right? So there's the actual plot. So there's the incident wave. Remember, it's got an amplitude of 4, not 8. It's delayed by 2 nanoseconds. Then we have a delay of 6 nanoseconds. And this guy's gotten multiplied by that minus 0.71429, which gives you a value of minus 2.857. So the oscilloscope first sees the incident wave sweeping past it. And then a little bit later, the reflected wave sweeping past it going backwards towards the generator. Okay. Was that an easy problem? But you could have done it on your exam, right? Some are shaking their head, yes, that's a good sign. Okay, yeah. Mm-hmm. Make sense?
Why is A1 again?
That's the voltage divider. That comes from looking at this 50, the Thevenin generator resistance, and this Z0, the first line. Because when you first launch the waveform on line 1, forget all of this, right? as far as the waveform is concerned, when it first goes on the line, this line might as well be infinite because it hasn't reached anything yet, right? Now, let me remind you that whenever you look into an infinite line, or I should say semi-infinite line, it's going to act like a resistor whose value is the characteristic impedance, right? The characteristic impedance is not a resistor. It's a number that characterizes the transmission line, right? Square root of L over C. But it is voltage over current for a wave going in the positive Z direction. So that's why it acts like a resistor, right? So just treat it like a normal resistor for the purposes of voltage divider, right? So this came from the usual voltage divider, right? 50 over 50 plus 50.
You got 8.333 ohms. That is the parallel of the 10 ohm resistor and the resistance load.
Yeah, so it's 10 in parallel with 50. The 10 is the fault resistor. That's in parallel with this 50, right? Now they have to be the same, but the 50 here means this 50 because the waveform is coming along, getting ready to hit the junction. You want to know what that waveform sees. It sees this in parallel with all of this. But remember, ignore this load because the waveform hasn't hit that yet. It's just first hitting the junction. When it first hits the junction, it's going to look into this line and see 50, just like the generator looked into line 1 and saw 50. That's where the A came from, right? Same principle. Okay, maybe I should have chosen this to be something different than 50 to avoid confusion, because they're both 50 here, right? Okay, but there's a 50 that gave you the A coefficient, and then there's a 50 that gave you this 50 here. That comes from line 2. Yes, this 50 in the parallel is the Z0 of line 2. This 50 in the A coefficient is the Z0 of line 1. Yeah.
So how can we disregard the resistive load?
Which resistive load? You mean the RL?
Yeah, RL.
Because when this waveform first hits here, it doesn't know that this is even here, right? It hasn't time to get there, right? If you're worried about what this waveform sees first hitting the junction, it doesn't care about this at all.
So it's like it's...
Right. That's what this gamma means, right? Yeah. Now, if you wait long enough, sure, the waveform in general would come down here, bounce again. There'd be a transmission coefficient, all that. It's not really going to happen in this problem because the load is matched to line 2, right? That's why I got rid of all these, right? Okay. Anything else on it? Okay. All right. Okay, so we're ready to start notes 9. And now we're still in transmission lines. We're going to be in it for another, maybe a couple of weeks or something like that. I don't know. But now we're changing gears and it's going to be transmission lines in the frequency domain. We're done with the time domain. That's all the bounce diagram and that kind of stuff, right? Some kind of waveform, the time domain is going down and bouncing around. Now you're in the frequency domain, the sinusoidal frequency, steady state frequency domain, or in other words, phasor domain, right? So that's the change of gears here, okay? Some pretty pictures of signals there. Okay. Now, first, I want to give some motivation. Question is, why is the frequency domain important? Okay. First bullet's kind of interesting. It says most communication systems, not all, but most communication systems use a sinusoidal signal. Now, the sinusoidal signal is usually modulated because that's how we carry information, right? So it's got, but the sinusoidal signal is the carrier, and that's the main wave that's put on the transmission line. Okay, it's modulated, fine, but it's the carrier wave that's really the sinusoidal wave that we're interested in. So just as an example, this might be what's called the baseband signal, maybe an audio signal, something like that. And you got a carrier. Now it could be, modulated with AM or FM. Could even be phase modulated. Those are 3 ways you can modulate a signal, right? But anyway, the main thing we're interested in is the fact that there's a carrier, there's a sinusoidal steady state wave, and all the theory we're going to develop is for a sinusoidal steady state wave. And so in other words, the phasor domain. The fact that in real life it's modulated, that doesn't really cause much concern. Okay? That's what the communication people worry about, but for us, it's just a sinusoidal steady state wave. null theory is applicable to a very good approximation, even though it's modulated. Okay, so it's a carrier wave we're talking about here. We'll say sinusoidal steady state. Okay, now there are some exceptions, like for example, Ethernet is one notable one where it communicates directly in baseband, meaning there's no carrier, like 100 base T or 10 base T. There's an example of internet protocols, Ethernet protocols where there's no carrier. Okay, but most communication systems are going to have a carrier. Now, certainly all wireless systems have a carrier, right? Because, you know, in a wireless system transmits out of an antenna, right? And the EM wave goes through free space and impinges on a receive antenna, like a cell phone antenna. Now, you cannot transmit a baseband signal, like an audio signal, out of an antenna, right? You know, as you learn in antenna theory, as we talk about antennas later, you know, to operate well, most antennas need to be a certain resonant length that's somewhere around maybe a half a wavelength in size or a quarter wavelength in size, right? So if you take like your cell phone operating at 2 gigahertz, something like that, you know, the wavelength is going to be so many centimeters, like 6 centimeters, something like that. So that's why the antenna on a cell phone is about this big, right? Okay, it can radiate a microwave signal good. But let's say you're trying to have an audio signal. Audio signal might be 10 kilohertz. What's the wavelength going to be? Right? Hundreds of miles, right? So you can't radiate an audio signal directly out of an antenna, right? A practical antenna. So obviously for wireless, you have to have a carrier, a microwave carrier, which is then modulated to carry the information, right? Now, if you're carrying information on a transmission line, it's different because an ideal lossless transmission line carries a signal at any frequency, any shape without distortion. We know that, right? Sawtooth wave, whatever you want. Okay, so the transmission line doesn't have that problem. It has other problems, right? The transmission line is lossy. The signal can attenuate as it goes down, and the loss can also cause distortion. So there's a trade-off there. But anyway, the bottom line is most communication systems do operate in the frequency domain with a carrier wave. Okay. Yeah, Chloe, go ahead. What comes in? Yeah, exactly right. Because if you like and that can be especially problematic on transmission lines. We have distortion of the signal, right? Because you can have like what's called intersymbol interference, for example, if there's too much distortion. Yeah, and so you have to do correction, or even put a repeater there to recover the signal and broadcast it again, right? Okay, that's reason number one why frequency domain is important. Here's reason number two why frequency domain is important. So reason number one is like a practical reason. Reason number two is kind of like a mathematical reason, but it's also very important. It says a solution in the frequency domain allows us to solve for an arbitrary time-varying signal on a lossy line by using the Fourier transform method. Okay, so now this gets into your signals and systems course. Have most of you taken that? Signals and systems? Okay. If you haven't, I apologize, but don't worry, you don't need it. This is just motivation, okay? But let me just talk a little bit about the frequency domain here and the reconstruction of time domain signals. I'll go through, I'll do an overview of the math in just a second. But basically, the bottom line is, by using the concept of the Fourier transform, we can solve for what happens on a transmission line, even if it's a lossy transmission line, with any kind of a time domain signal applied to it. Okay? Now, let me remind you that in the time domain that we just finished talking about, we only have an exact solution for a lossless transmission line. Remember that? Okay, so if I have a real life coaxial cable with loss on it, and I put some kind of a pulse or something on it, I can't use the bounce diagram and all that, not if it's lossy, right? That's only for a lossless line. Okay, for a lossy line, we can use a more powerful method based on the Fourier transform. And I can then put a signal on any kind of a transmission line, no matter how much loss it has, and reconstruct the signal. Now, if the line happens to be lossless or low enough loss that you can treat it as lossless, this is overkill, right? You might as well use what we just finished talking about, the bounce diagram and all that kind of stuff, right? But if the loss is important, then the Fourier transform method allows you to solve for even an incredible amount of loss on the line. Okay, so it's a really more powerful, more general method of solving the problem. Okay, let me overview it a little bit. Okay, and this should make sense if you've had your signals course. Okay, so here's of course Fourier, a famous French mathematical physicist. Now, I'm not sure if this agrees with the notation you use in your signals and system course. There's a lot of books, different books have different notations when they deform the transform, inverse transform. Okay, this is how I'm going to do it. So if you have a signal, like a voltage signal V of t, here's how I define the transform. So notice I put the minus there. And here's how I reconstruct the signal with the inverse transform. So the plus here, so minus here, plus here, and then a 1 over 2 pi. Again, some books put a plus here and a minus here. Some books put the 1 over 2 pi here. Some books split it and put 1 over square root of 2 pi in both places, all kinds of notations, right? Different conventions, but I'm going to stick with this convention, okay? Now, it turns out that for a physically realizable, in other words, real valued signal, and remember, in the time domain, voltage is a real function, right? It's not complex, it's a real function. That's what I mean by physically realizable, real valued. Then you can take this equation here and use the property that the Fourier transform at negative frequencies is equal to the conjugate of the transform at positive frequencies. Okay, I won't take the time to prove it, but if you look at this definition of transform, it's not too hard to prove, taking the conjugate of both sides. But anyway, if you use that property, then you can show that this form of the inverse transform is equally equivalent to this form, which is nice. So notice this one has, so the integral goes from 0 to infinity instead of negative infinity to infinity. And it's pi instead of 2 pi. Okay, and then there's a real part here, Okay, all right. There it is one more time. Now, I just want to point out, and I know you're probably familiar with this from your signals course, but I'm just kind of reviewing here. I want to point out that if you look at this formula for the voltage reconstructed from the inverse transform, look at what I've highlighted in blue. Now, by the way, usually a mathematician would put the d omega outside, right? That's the usual calculus convention, but I snuck it inside just for convenience. So notice I'm writing it like this. Now look at this term in parentheses, and then notice it's got a real part. See what that reminds us of. The real part of something in parentheses in blue, e to the j omega t, right? The real part of something, e to the j omega t. What's that something? Ah, it's a phasor, right? It's a phasor, okay? So that gives us a clue. So the input, if this is the input to a system, then notice that the input signal, call this an input signal, is thought of as a collection of phasors. That's what the integral is, the Riemann sum and the limit, right? It's like a collection of phasors. And if we know what one phasor does, in other words, if we know what a system does in the frequency domain, in the phasor domain, then all we got to do is multiply this by the transfer function, as we call it, which tells us what a single phasor does. And then we can get what the output signal is. Okay, so that's basically the physics here. So if you think of this as an input signal, it's resolved as a collection of phasors. Okay, now each phasor corresponds to a different frequency. Notice that you're integrating from 0 to infinity in omega. So frequencies going all the way from 0 to infinity, symbolically, like here's different components, different omegas here. Whatever omega is, here's that transform, so it's some complex number. But anyway, so different frequencies, they look like this, different amplitudes too, different phases. But if you believe in the Fourier transform or the inverse transform, what it tells you is if you take all these phasors corresponding to all these different frequencies like this, and you add them all up, you get back something like this, which could be your input signal. That's the magic of the inverse Fourier transform, right? That's what it does for you. Okay, it's amazing. Now this pulse only exists from here to here. Each sine wave is a steady state sinusoidal wave that goes on forever, right? On forever. All right, that's why you can use phasors. But when you add them all up, you get this thing that looks like the original waveform. But the important point is that any omega, this thing in parentheses can be interpreted as a phasor. Okay. All right, here's an example. If this is like a pulse with amplitude W, and if you just by brute force, take the mathematical expression for this as 1 between here and 0 elsewhere, it's not too hard to show that the Fourier transform is this, where this is the sinc function. So this is like the spectrum, the Fourier spectrum of the pulse function, right? It's maximum at 0 frequency, and then it kind of dies down. It's got negative omega, got positive omega. But remember, if I use this form here, I only need the positive omega. That's one thing I like about this form here. See, the inverse transform here goes from negative infinity to infinity. When you write it like this, omega just goes from 0 to infinity. So then it's convenient to interpret omega as a frequency, right? Omega is 2 pi f. F is always positive, of course, right? F is 1 over your period, right? So that's why we like this form here. That's positive frequencies, and it makes sense. That's your phasor, okay? So again, here's a system. Now for us, this is going to be a transmission line. But really, according to system theory, this could be any system. And it's got what's called a transfer function, often called H. Okay, now if you're in the phasor domain, okay, what does transfer function mean? Let's review that. So in the phasor domain now, you've got an input phasor voltage, capital VN, output phasor voltage, capital V out, and then the definition of transfer function is just V out over VN, right? Okay, So, or in other words, V out is V in times the transfer function. That's how you use a transfer function, right? In a system. Okay. So now remember that in the phasor domain, we just said that the input signal is a collection of these phasors. If each phasor just gets multiplied by the transfer function to get output phasor, then it's easy to go from input signal to output signal. This guy here just gets multiplied by the transfer function, right? That's all that's going to happen. So what happens then is that's pretty much all there is to it. In the time domain then, here is what the output of a system is going to be. Notice the lowercase v, time domain, output signal due to an input signal. So notice that's the same equation as this, except I've just multiplied this by the transfer function, right? You see that? Okay. So as a summary page, if I have an input signal in the time domain, and I want an output signal in the time domain, any linear system, the output signal comes from the Fourier transform of the input signal after multiplying by the transfer function, which is defined in the phasor domain, and then carrying out this integral. Okay. So that now this is the mathematical basis behind why I said in bullet number 2 that with the Fourier transform, we can be more general and solve any kind of a lossy transmission line problem, right? It applies to any system. Lossy transmission line is just one special case, right? So if I can get the transfer function for it, I can solve for the output function in the time domain. Okay, so you believe that? It's a really powerful result in basic signal theory. Okay, does it make sense? You've seen it before, right? Probably. Okay, but very, very powerful result there. Now, if you have just a transmission line going from input to output, as we'll see very soon, the transfer function is going to be very simple because in the frequency domain, the wave travels along the transmission line in the positive z direction as just what we'll call e to the minus gamma z, where gamma is called the propagation constant. So this transfer function will be really simple. Okay, but even if it's a complicated system, as long as you know the transfer function, we can go from input to output. Okay, lossy transmission line, anything. Okay, and you remember when I was talking about that microstrip line on the circuit board, and I stole some results from the microwave engineering class, and it showed you how a digital pulse loses amplitude and distorts as it goes down a microstrip line on a circuit board. Do you remember that? Okay, that's where this came from. You know, that was like the class project in microwave engineering. They had to implement this in MATLAB and actually study the pulse going down the microstrip line. Okay, that's where it came from. All right. Okay. All right. Anyway, now I'm ready to get into the actual transmission line part. Any questions out there? There's your motivation and background. Any questions on that? Okay. All right. Now let's go back to the beginning with the telegrapher's equations. And here's a model of a transmission line. And revisit it now with interest in going to the frequency domain. Okay. Now, we already saw this equation before from the telegrapher's equations. Now, let me just remind you, telegrapher's equations are two coupled set of first order differential equations, one for voltage, one in current. They're both in terms of each other. And we showed how you can take the derivative one and substitute in the other one and get a single equation. It's a second order differential equation for the voltage. Go back and look at that if you want to see that again. Okay, but this is the final second order differential equation that voltage on the transmission line obeys. I'm not making any assumptions, so I'm leaving the R and the G. So it can be as lossy as you want. Okay, current obeys the same differential equation, but let's just work with voltage. Remember the reference directions, by the way. We already know that, but remember the reference directions. Okay, and remember that, of course, always we assume equal and opposite current on the bottom line, but I don't keep showing it, right? Remember that. Okay. What we call the balanced or differential mode, the mode that we normally operate in. Okay, well, we all know that when you have, derivative with respect to time, it just goes to j omega in the frequency domain, right? In the phasor domain. So it's pretty simple. Now, notice the change in notation. Lowercase v was time domain, uppercase v is phasor domain. So uppercase v is not a function of time. It's phasor voltage, not a function of time, but it's complex, right? Just like a phasor normally is, right? Okay, so we change the notation, and wherever you see a time derivative, you put a j omega, see? Now, this had second order derivatives with respect to time, so of course it goes to j omega twice, and of course j squared is simply -1, right? Okay. Now, I then rearranged and put everything on the right-hand side except for this term right here. Everything else went across, and that's why the minus signs went away. Okay, but this is two minus signs, so But so it becomes a plus sign, but then went across, so a net minus sign. Anyway, so here's after rearranging. Now let me work with that a little bit. It looks kind of messy, but let me see what I can do with that. I want to see if I can simplify the right-hand side a little bit because it looks kind of messy. Okay, there it is again. Now, if you stare at the right-hand side, and please do, you convince yourself that the right-hand side here it is again, now it's the left-hand side, can be written in a nice factored form. So this right-hand side right here can be written in a factored form like this. Just stare at this equation and see if you believe it. Okay, like for example, RG comes from this term comes from this times this, but then you also have this times this and this times this. You see that? Okay. Now, okay, it makes it look a little simpler, but there's another reason why that's kind of a nice factorization. These two terms have a very nice physical meaning by themselves, as shown here. R plus J omega L. Let me go back to the model. R and L, what's the impedance of the inductor? J omega L, right? So R, now remember, R and L are per unit length. So R plus J omega L is the series impedance per unit length. You can interpret it that way if you want. Okay? So why not call it that? And similarly, Y plus J omega C would be the parallel admittance per unit length. These two guys in parallel. Remember, the admittance is J omega C, of course. Right? That's just from basic circuit theory. So let me give them a new name. Let's just say Z, capital Z, usual formula for impedance, is now the series impedance per unit length. It means this. And capital Y is the parallel admittance per unit length, the usual symbol Y for admittance. It means this. So look how simple it now looks. Okay? Now it looks a lot simpler. Now remember, Z and Y, I'm at some frequency, omega, 2 pi f, whatever you want to give me. And at some frequency, capital Z and capital Y are just known complex numbers. Now you give me a certain transmission line like a coax, I can calculate the R and the L using this formula I showed you before, right? So if I do that, these are known complex numbers. So this thing here is a known complex number. Okay? All right, so there's a summary page before I go on. Here's resistance, parallel admittance, differential equation. Looks very, very simple now. There it is one more time. Now, even nicer, I will define something called gamma. I first define it by actually defining it squared, gamma squared, but gamma will be called the propagation constant. The definition of gamma squared is just this term in parentheses, zy. Okay, that's this. So then we have this, and now it's, I don't think you can even get much simpler than that. So very, very simple differential equation, finally simple enough. We can guess the solution. The solution is just a combination of e to the minus gamma z or equally valid e to the plus gamma z. Okay. Now, if you wanted to, you could also say some combination of hyperbolic sine of gamma z or hyperbolic cosine of gamma z, but let's don't do that. Let's just stick with this form here. Some combination of either minus gamma z, either plus gamma z. A and B are just two arbitrary complex coefficients. Okay. Now, very soon, a couple seconds, we'll give the interpretation that this means in the phasor domain, the wave that's going in the positive z direction, and this is like a reflected wave coming back going in the negative z direction. Okay, we'll see that in just a second. Now, let me emphasize that this is an exact solution. I did not neglect loss. I did not make any approximation, so this is an exact solution in the frequency domain. Now, let me emphasize one more time that if I just had nothing but, a generator, transmission line, and a matched load at the end, there wouldn't be any reflected wave, that transfer function would be just this, right? E to the minus gamma z. That's all it would be, actually. But anyway, so we have an exact solution in the frequency domain. That's really nice. Okay. Now, one more comment. So we have gamma squared, right? Gamma squared is this, right? This is, of course, a complex number. Gamma squared is a complex number. We take the square root to go back to gamma, right? Now, I'm going to say that the correct square root is, and we'll justify this in a second, the correct square root is what we called, remember this from our discussion weeks ago? The principal square root, remember that? The radical sign means the principal square root. I'm going to define gamma. The way I'm going to define it now is with the radical sign. So the principal square root of just capital Z times capital Y. And now the official name is again called propagation constant. and the units are said to be 1/meters. Okay. We already talked about this. Just allow me a 30-second review. If you have any complex number, like in polar form, then the principal square root cuts the magnitude down by square root, divides the phase angle in half. But for a principal square root, we make the agreement that the angle is between minus pi and pi inclusive. And so cutting the angle down by half, it's between minus pi over 2 and pi over 2 inclusive. And that in turn means that the square root, principal square root of any complex number is greater or equal to 0. In other words, the principal square root lies in what we call the right half of the complex plane. So gamma, the propagation constant, lies in the right half of the complex plane. Right? Now, if we take gamma and express it in rectangular form, the real part is called alpha, and the name is the attenuation constant. You could say the units are 1/meters. That's not wrong, but people like to put the fictitious unit meters in there. And so we say, engineers like to say the units are meters per meter. Beta is called, the imaginary part, beta, is called the phase constant. And again, you wouldn't be wrong if you said the units are 1/meters, but people like to put radians in because it's a phase. I mean, radian is really dimensionless, right? But we like to say beta is radians per meter. So that's the official units on all three of them. So gamma is alpha. So if I give you, a transmission line, like a coax, give you all the dimensions, give you the epsilon, give you everything, you can calculate the RLGC, you plug in here at any frequency, you can take this square root, you can get the complex gamma. I'll work an example later. And then you take the real imaginary part, so you've got the alpha and the beta. Okay. Now, remembering what I said about the principal square root, okay, so the real part of gamma, which is called alpha, is greater than or equal to 0. So the alpha is never negative. Alpha is never negative. Okay. And that is why, in fact, we interpret this. Let's go back. Why we interpret this term here as a wave going in the positive z direction. So just visualize. Okay, gamma is alpha plus j beta. Right. So when I plug in, and I just worry about the amplitude, it's going to be e to the minus alpha z, right? This is going to be what? If you look at the alpha part, this one here is going to be e to the plus alpha z, right? Remember, principal square root, so alpha is not negative. So alpha has a positive real part. So this is the wave that's decaying as z gets bigger, right? This wave is increasing as z gets bigger, right? So this is an incident wave. If it's going in the z direction, it's a lossy line, you expect it to be losing energy, right? Because of conductor and dielectric loss. So it makes sense. It's getting weaker as the wave goes down. That's what the alpha does. That's what's called attenuation constant. The reflected wave is going this way, negative z direction. So of course, it's going to get weaker as it goes in the negative z direction, which is another way of saying it's growing in the positive z direction, right? It makes sense for a reflected wave. Does that make sense? Okay. Okay. For the lossless case, okay, it's just a special case. We can handle general lossy case now, but if it's a lossless line, we just get rid of both the R and the G. That's what a lossless line means. No, no resistive loss in the conductors, no dielectric loss either. Okay, now you have the square root of j omega times the j omega. So you get a net omega, and you get a square root of -1. Okay, and then remember our agreement with principal square root. If I go back here, so if I take the square root of -1, okay, so what's the phase angle of -1 going to be? We call it pi. Cut it in half, pi over 2. E to the j, pi over 2 is j. Okay, so this goes to j, plus j, according to our agreement with a principal square root. So now remember, gamma is written as alpha plus j beta. Remember that. Now gamma becomes pure imaginary. There is no alpha, right? So alpha is 0, and beta is everything in front of the j. So beta is this. Okay. It makes sense. If it's a lossless line, why would you have an attenuation constant? The wave is not attenuating, right? So alpha is 0. But of course, there's a beta, because beta controls the phase of the wave. The wave is moving at the speed of light, basically, as we'll see. So, it's going to be changing phase as it goes down, but not attenuating if it's a lossless line. Okay. All right, here's I kind of said a lot of this already with words, but so let me go over it one more time. Here's a physical interpretation of the waves. So plus is the same as we did in our time domain notation. Plus means a wave going in the positive z direction, forward direction, and minus means a wave going in the reverse direction or backward direction or a reflected wave, different ways of saying the same thing. So this is the forward wave. This is like the backward of the reflected wave, going the backward direction of the reflected wave. Okay. And again, substituting in gamma is alpha plus J beta. I probably should have gone to this slide when I was talking, but oh well. So here's the forward wave and here's the reverse wave. Again, you see what the attenuation constant doing, right? So forward wave is decaying in the positive Z direction. This one's growing in the positive Z direction or decaying in the reverse direction. And again, the beta is giving you a phase shift, right? This is a J there. This is controlling the phase of the wave, right? Okay. All right. Now, also, let me introduce alternative notations. We'll see the alternative notation more a little bit later, not so much in this set of notes, but it's good to introduce it now, I guess. So there's two notations that's very common in EM when you're talking about waves on a transmission line in the frequency domain. Well, not only waves on a transmission line, but waves in a waveguide, waves propagating through space. Whenever you have waves in the frequency domain traveling from point A to point B on any kind of thing, there's two different notations. So one is what I call the propagation constant notation, not to be confused with this, which sounds similar, called the propagation wave number notation. So gamma, remember, is called the propagation constant. And we know how to calculate it, square root of R plus J omega L times G plus J omega C. So anyway, it's a complex number, attenuation constant, and then phase constant. But anyway, then what's called the propagation wave number is defined, it's called Kz, if the wave is going in the Z direction, as it is here. It's beta minus J alpha. Now, if you compare the two, then you can see that they're related simply by gamma is J Kz. Just multiply this by J and you get this. Because remember, J times minus J is 1. So you can say gamma is J Kz. Or if you multiply both sides by minus J, you can say Kz is minus J times gamma, whichever way you like. Okay, but they're related by a J or minus J. So notice the alternative notations. You can say that a wave going in the positive Z direction is some constant, e to the minus gamma Z. That's what I just did a minute ago. Or if you want to substitute in this equation here, e to the minus J KZZ. Whichever notation you use, they're both equivalent to saying this. You got an attenuation term and you got a phase shift term. But two different notations, okay? But for right now, let me stick with this one. In later notes, when we're doing Smith charts and various things like that, it'll be more common to use this notation, okay? In fact, most people, including me, prefer the propagation wave number notation when you know you have a perfectly lossless line. But for a lossy line, I kind of like the gamma notation. That's just my personal preference. But anyway. Okay, now let's look at the forward-going wave for a second and bring out a little bit more of the physics of it. It's going to work almost identical for the reflected wave, but let's just do the forward wave. So here's the general form of it. Remember, it's e to the minus gamma z. So I just separated out into an amplitude term and a phase shift term. Now, A could be a complex constant itself in the phasor domain. I mean, sometimes it might be real, but just to be as general as possible, it could be complex too. So just to be as general as possible, I assume this complex and put it in polar form. Okay, so then doing that, here's the most general form in the phasor domain of a voltage wave going in the Z direction, for example, on a transmission line, right? Okay, if we have an attenuation constant and we have a phase shift constant beta. Okay. Now remember, maybe redundant, but let me say one more time. Obviously, this is not a function of time. We're in the phasor domain. It's only a function of Z, right? So it's complex because you have a phase shift here from the A, and you also have this phase shift term, right? So everything's complex, but not a function of time in the phasor domain, right? Okay. Now, of course, to go back to time, now this is the notation I used before, lowercase. Now it's a function of time. This is the forward wave and going down the line, which is a function now of Z and time. As usual, the usual golden rule of phasors, right? Real part of phasor, e to the j omega t, right? So just take all this and plug into here, right? And then take the real part. Now, when you do that, you can pull out of this curly parentheses here anything that's already real, like you can pull out the magnitude of A. You can pull out the attenuation term because that's real. So just pull it out. And then what's left inside, the real part is just going to be this phase shift term and this beta term, right? So when you multiply by then e to the j omega t and take the real part, there's three things, this, and this. So then from Euler's identity, just cosine omega t minus beta z and then plus phi from here, right? So that's what a sinusoidal wave looks like going down the line. So just imagine you've got like a coax or something, and it could have loss. It's a real life coax. And now you're putting a signal generator at the left end, which is putting out some pure sine wave, whatever you want, 100 megahertz, 2 gigahertz, whatever you want, and you're watching that sine wave, that single frequency sine wave go down the lossy coaxial cable. This is what it's going to look like in the time domain, okay? That's a mathematical expression for it, okay? Now, here's a snapshot of it. We freeze time. Let's just say t equals 0 to be convenient. Doesn't have to be, but let's just say, okay? And so we're just plotting this, just getting rid of this term because we're putting t equals 0. So you're just plotting basically what looks like kind of a cosine, right? It's oscillating as you go in z because of this phase shift term, beta z, right? But it's also losing energy because of the loss on the coax, and that's taken account by this attenuation term, right? So notice that this waveform has what I'll call an envelope, which is described by this term out in front, which I put in blue here, magnitude of A, e to the minus alpha z. That's like the envelope, and then the actual time domain signal, the time domain signal plotted versus z is then the squiggly black curve oscillating but staying within the envelope like that. Okay, does that make sense? And why is it getting smaller? Because of the loss, right, on the coax. Okay. Now, we'll define what we call wavelength. Okay. Now, even in the most general case of a lossy line, we can still define a wavelength. Now, normally, okay, let me say this. If there's no loss, then this envelope, this blue dashed line, would be a perfectly straight horizontal line. Okay. In that case, you're just plotting a pure cosine, so it goes back to where it started, back to where it started, back to where it started. And then in that case, wavelength would be easy to define. It's just the distance between one crest and the neighboring crest, both of equal heights. Now, because of the loss, the envelope is making these crests get smaller and smaller, right? Here's a crest, here's the next crest, here's the next crest. But that's okay. In the lossy case, we still define wavelength. And the wavelength is still defined to be the distance between one crest and the next, even though this one has lost energy, right? It's lower. So that's the definition of wavelength. The distance in meters it takes for the waveform to repeat itself when you plot like this. That's the wavelength, okay? Even though it's losing energy, okay? Now, the wave is going to repeat when that cosine wave repeats. Now, this is making it lose energy, but if this will look at where the crest appears, that's coming from the cosine. Remember, t is fixed, so as I'm plotting versus z, it's this that's changing the phase, right? So it's going to repeat when this thing here changes by 2 pi. That's when the cosine repeats, right? When beta times z changes by 2 pi. Whatever. So in other words, the wavelength is going to be whatever distance z it takes to make beta times z be 2 pi. That's when this term is going to go back to being 2 pi, repeat by 2 pi, right? So z is equal to lambda, beta times z is equal to lambda when the product is 2 pi. And then it's obvious that you get this important relationship right here. Beta is 2 pi over lambda, one of the fundamental equations in transmission line theory in the frequency domain. The phase constant beta is 2 pi over lambda, the wavelength in meters. Okay? And you can say the units of 2 pi are radians, so you can see units of beta are radians per meter. Okay? Now, you can use this equation in a couple different ways, okay? So if you already know lambda, obviously you can find beta. If you already know beta, you can of course find lambda, right? Okay. Now, if you give me all the parameters of the coax, remember, let me remind you, and the frequency, I can calculate RLGC using those formulas we had before. And so I can calculate gamma, square root of R plus J omega L times G plus J omega C. So give me all the parameters of the coax and the frequency, I can calculate gamma. And remember, gamma is alpha plus J beta, so I can calculate beta, right? And so then I can calculate now lambda, because from this equation, lambda is 2 pi over beta. So here it is written out in mathematical form. So lambda is 2 pi over beta, beta is the imaginary part of gamma, and gamma is that principal square root of R plus J omega L times G plus J omega C. So here's the final mathematical equation. Lambda is 2 pi over the imaginary part of this principal square root of this term here. That makes sense? So now I'll work on an example later, but I give you any coax and all the dimensions and everything. And then given a certain frequency, so you know omega, you can calculate the wavelength. The distance, again, it takes to repeat. Okay. Oops, sorry. Here's a special case, the lossless case again. Now, no transmission line is 100% lossless in real life. But if it's a really low loss line, you might be willing to accept and call it a lossless line. Okay, but anyway, if it's a lossless case, special case, let's see what the lambda becomes. Remember, this is always true, 2 pi over beta. Now, as I said a minute ago, for a lossless line, alpha is equal to 0 and beta is omega squared of LC. We saw that a minute ago. Okay, and omega is, of course, 2 pi f in hertz. 2 pi's cancel, so you can write it like that. Now, we also, you remember I told you before that for any transmission line, L times C is equal to mu epsilon. You remember that from a couple of weeks ago? Okay, so that's true for any transmission line. I only proved it for the coax, but it turns out to be true for any transmission line. L times C is equal to mu epsilon. So that's the permeability and the permittivity of whatever that filling material is inside the coax or between the 2 wires of a twin lead, whatever, right? Okay. If it's a microstrip line, like in that one homework problem, then you got to use something called epsilon effective. Remember that? Okay, but anyway, so 1 over square root of mu epsilon is what we call the speed of light in the dielectric. So there's no way of writing it. Okay, and also we can say the speed of light in the dielectric, you know, because this thing here can be factored into mu 0 epsilon 0, and then pull out square root of mu r epsilon r, and 1 over square root of mu 0 epsilon 0 is the speed of light in vacuum. So you can write it like this. Okay, another way you can write it, I'm giving you all those ways you can write it. C over F is what we call the wavelength in free space or vacuum. Okay, all right, so all these different ways you can write it. Okay, and now here's a new notation. Okay, so lambda on the transmission line is equal to this, and this can be recognized as what we'll call the wavelength in the dielectric material making up the transmission line between the 2 conductors, like the Teflon and the coax or polyethylene, whatever it is. So D reminds us not to forget that this is wavelength not in free space. That's lambda 0, right? Lambda D is the wavelength in the dielectric, which is lambda 0 free space divided by the square root of mu r epsilon r. Okay, so summary page. Here's what we know so far in the frequency domain. At any frequency, the wavelength on a transmission line is on a lossless line is lambda D. What is lambda D? Very simple formula for a lossless line. Lambda 0 in free space over square root of mu r epsilon r. Now remember, for most plastic materials, mu r is 1, but anyway. And then lambda 0 is the usual wavelength in free space. Here's the speed of light. So very simple formulas. Make sure you have those memorized. Very simple formulas for a lossless line. Now remember, if it's a lossy line and you're not willing to accept this approximation, then there's no simple formula for lambda. Okay, then what you got to do is go back to this. Right? It's easy to do on MATLAB or your calculator, but that's what you got to do for a lossy line. If you're willing to accept that it's a very low loss line or a lossless line, then very simple formulas for lambda. Okay, make sense so far? Okay, all right. Let's go back and revisit the attenuation constant. Okay, here's my snapshot again. Let's say it's equals 0. And now, so we already talked about the cosine part. Now this part is controlling the amplitude, right? How the wave is attenuating, and that's why alpha is called the attenuation constant. Okay, so alpha is the real part of gamma. Gamma is alpha plus j beta. So once I give you all the parameters of the line and you calculate, take the square root and get gamma, and now you take its real part to get alpha, and that's the alpha that goes in here, the attenuation constant. Okay. All right, that makes sense. Now I'll say a bit more about it when I talk about dB a bit later, but for now, let me move on here. Another thing that's important is how fast is this sinusoidal wave moving on the line? Okay. Now, for a lossless line, the conclusion is always going to be that the signal just travels the speed of light, what we call CD. But this could be a lossy line. In the most general scenario, how fast is a signal moving on the line? That's still in the phasor domain. So I'm talking about a sinusoidal steady state signal coming out of a function generator, putting out a sine wave, for example. And how fast is that sine wave moving down the line? Now, the official name of that is going to be phase velocity. How fast does a single frequency sine wave coming out of a generator move down the line? That's called the phase velocity. That's the official name of it. Okay, now let's visit that. Now, here's the form of the wave. Now, you could have as much attenuation as you want. I don't care, but in this figure, I kind of ignored it. See, in this figure, I drew the waveform not getting weaker in the z, it's going up the same level, crest to crest. So the math doesn't really care, but in the figure, I just pretended that there's no loss for simplicity, as I said there. So what I'm going to do, now just imagine I'm tracking this wave, sinusoidal wave, moving down the line, and I'm giving you two snapshots. The blue is a snapshot of what I'll call T1. I wait a little bit longer time, and the snapshot is then taken at T2, which is the red. Because it's moving, it's gone from here to here, going from time T1 to time T2, of course, right? Now, I'm going to track the crest of the wave. The crest of the wave is the point where the whole argument of the cosine has a phase of 0, or you could say 2 pi, right? Okay, so I'm tracking the blue dot as I'm tracking the crest of the wave. I'm tracking the point of constant phase, hence the name phase velocity, right? How fast is the crest moving? The crest is a point of constant phase, right? That's where the terminology is coming from. So think of this blue dot, the crest, moving with a velocity called Vp, which is what we call the phase velocity. So what is it? What is it? Okay. Now it's easy to calculate. Let me do that. So point of constant phase. Okay, so that's where all this is a constant. Now, if you want the crest, then set it equal to 0 or 2 pi. Could be some other point. You know, I could be tracking the bottom, the negative crest. It doesn't matter. But anyway, I'm tracking a point of constant phase where all this argument in parentheses is a constant. Okay, so I'll set this thing equal to constant, take the phi across the equal sign. It's a constant already. So you get omega t minus beta z is minus phi, just a constant. Whatever that is, I don't care. Anyway, the easiest thing now to do, see the velocity is, of course, derivative of z with respect to time. Delta z over delta t, right? That's velocity. On the limit dz over dt, derivative of z with respect to time. That's velocity, right? So one thing I can do to try to solve for that is just take the derivative of both sides with respect to time. What's the derivative constant is gone. Here, derivative just gives me omega. Now, beta is a constant, but then the derivative operates on the z and gives me back dz by dt. So there's our fundamental equation. Take this term across the equal sign, okay, and then divide both sides by beta, and you got your answer really. So dz over dt is omega over beta, and this is the phase velocity. So we've now derived an important relationship, important equation in transmission line theory, valid for any transmission line at any frequency. The phase velocity is omega over beta. And that's exact, no approximations. It holds even for a lossy line. But remember, for a lossy line, for calculate beta, you got to go through this, right? In general. So you got to do that on your calculator or MATLAB. It's not trivial. But anyway, once you have beta, you plug in here at some frequency omega, and that's phase velocity. Okay? That's how fast that sinusoidal is moving. Now, let's do a lossless line, or one that's low enough loss we're willing to consider it to be lossless. So it simplifies greatly. So then, as we derived a few minutes ago, alpha 0 and beta is omega squared of LC. Omegas cancel. Oh, that's nice. Omega canceled. What does that mean? On a lossless line, the phase velocity does not depend on frequency. It's a pure number, pure constant. Okay? If it's a lossy line, the phase velocity will in general depend on frequency, right? So in general, if it's a lossy line, remember beta is coming from this messy equation here, right? And you see it's got omega in it, right? It's really messy equation, it's got omega in it, right? So when you take this ratio on a lossy line, omega over beta, it's in general going to come out to be a function of frequency. But for a lossless line, it's just 1 over square root of LC, so it's a constant. Now, I may say this in later notes, but let me just make it a point now before I forget it. There's one interesting ramification of this. So for a lossless line, the phase velocity is just a pure constant, doesn't depend on frequency. So one thing that does for us is it says that for a lossless line, a signal going down a line, even if the signal contains multiple frequencies now, it's not going to distort or change shape. Why? Because all Fourier components travel at the same velocity. Remember, a signal like a pulse is made up of the Fourier spectrum of frequencies, right? If they all travel at the same frequency, the whole thing just moves down and doesn't change shape. If you're getting like a rectangular pulse at the input of a lossy coax, I can use that Fourier transform method to construct the output signal, right? But if all those Fourier transform components corresponding to different frequencies that travel at different velocities, one going like this, one going like this, they get all scrambled up at the output, and that's what causes distortion. The signal changes shape, right? So from Fourier theory, in this equation here, it agrees with what we learned so far. A lossless transmission line is not going to distort a signal. Right? Now, we knew that from our time domain discussion, bounce diagram, all that kind of stuff. Now we see it here again. Okay, very important principle. But a lossy line, in general, will distort the signal. Okay, like I showed you from the microwave engineering course. Anyway, let me go on here. Now, also we know, remember, that for any line, L times C is mu epsilon. And this could be written as 1 over speed of light in the dielectric squared, because speed of light in the dielectric is 1 over square mu epsilon. So another way we can write this nice equation is that for a lossless line, the phase velocity is just the speed of light in the dielectric. Okay, and there's different ways of writing it. There's one way. Here's factoring out the mu 0 epsilon 0 and recognizing that 1 over this is the speed of light in vacuum, so you can also write it like that. Okay, so lossless line, phase velocity is just a constant, does not depend on frequency. And what is it? It's just the speed of light in the dielectric. Does that make sense? But if it's a general lossy line, you got to go through this. It'll be frequency dependent. Okay. Now, sometimes you'll meet something. I'm not really going to do too much with it in this course. You talk more about it in the microwave engineering course, but it's probably worth mentioning what it is. There's something called the group velocity. Okay, what the heck is that? Now, phase velocity is the velocity of one sinusoidal signal, one sinusoid at one frequency, right? Your function generator is putting on a sine wave at 1.5 gigahertz. You're just tracking that one frequency wave as it goes down the line. That's the phase velocity. Group velocity is the velocity at which a pulse or a signal will travel on a transmission line. Okay, and you can go through analysis thinking of a pulse as a collection of signals from the inverse Fourier transform and do some analysis and do some approximations. That's done in the microwave engineering course. I'm not going to do it here, but the final bottom line you can derive is this equation here. The group velocity, it looks very similar, the derivative of omega with respect to beta. So phase velocity was omega over beta. The group velocity is the derivative of omega with respect to beta. Okay, so that's the important conclusion here. Okay, now remember, if it's a lossy line, there'll be some distortion of the signal too. It's not going to stay just looking nice and sharp like this. But nevertheless, if you track, let's say, the middle of it, and look at how fast it's going, that's the group velocity. Now, if it's a lossless line, then it's easy to show. Okay, sorry, the equation is getting kind of cut off here, but anyway. So remember, for a lossless line, beta is omega times the square root of LC. So it's a linear function. So it's easy to take the derivative of omega with respect to beta, or you can take the derivative of beta with respect to omega and then flip it upside down. But anyway, it's easier then for a lossless line, we just have this linear relationship to prove that the two are equal. So group velocity, phase velocity become the same thing, just the speed of light in the dielectric. Okay, because this is a linear equation here. Okay, so it's got a constant slope. So omega over beta is the same thing as d omega over d beta. Okay. So for a lossless line, there's no distortion, and a pulse will travel at the speed of light just like a single frequency will. But for a lossy line, it's not quite so simple. Okay. All right. Now, engineers like to talk about dB, as you know. So let me go ahead and mention about dB here. Okay, this is talking about attenuation. So you got like a lossy coax running across the campus or something, across a city or something like that, or across a building. You want to know how much attenuation is going to be going from the generator to the load. How many dB are you going to lose? Very practical question, right? Okay. All right, so here's the voltage wave going, let's say in the forward Z direction, different ways of writing it, but I'm going to focus on this term, given the attenuation. Now, here's the dB and the gain, as we call it, the gain in dB going through a device. Like you could, now this could be any device. You could have an amplifier or a filter. I say, if I say gain, I'm thinking of it like an active device, but what's the gain in dB? 20 log 10 magnitude of voltage at the output or voltage at the input. Z is called the output. 0 is where the generator is, called the input. Okay. Now remember that that we know how the wave behaves, and don't worry about the phase term, right? And the A is just going to cancel out. So really, when you put in here, all you're doing is looking at e to the minus alpha z over e to the minus alpha 0, right? So just like this. Okay. Now, as the wave goes down the line from start to finish, this is going to be a number less than 1, so the log is going to be negative, which makes sense because this is how you define gain of a device. It's going to be negative because the line's losing energy, right? The output's weaker than the input, of course, right? Okay, but anyway, Now, it's convenient to use just a log identity. You can look this up in a math table, I guess, a math handbook, but there's a nice little log identity that says log base 10 of anything is natural log over log 10. Okay, so why don't we take advantage of that? So 20 log 10 of this thing, which is what I need right here, 20 log 10 of it, can be written as log of it divided by log 10. Now you see why that's convenient, because now I've got log of e to the something, right? The log undoes the e, of course, right? So you just get e to the minus, I'm sorry, you just get alpha minus alpha z. Okay. All right, and then just rearranging it slightly, pulling out the z, it looks like this. Now, it makes sense if there's a negative sign, because again, gain's going to be negative. You're losing energy as you go from start to finish on the lossy transmission line. So I'm going to define attenuation just to be the negative of the gain, right? Attenuation is always going to be a positive number. So if attenuation ends up being something like 5 dB, then that means the signal has lost 5 dB in going from start to finish. So it's the same equation, just get rid of the minus sign there. So attenuation is this, and it's in dB per meter. And if you want to calculate 20 over log 10, I invite you to do it. And it comes out to be this interesting number. I always thought this is kind of a funny looking number, but anyway, 8.686. So at least if you keep 4 significant figures, it's just 86, 8.686. So it's kind of easy to remember. Okay, but anyway, so that's attenuation in dB per meter on any kind of a transmission line, really on anything, but we're talking about transmission lines. Now, one nice thing about working with dB is notice that it's got a fixed value. I mean, alpha is just some fixed number, right? So it's got a fixed number in dB per meter. So if you want to know that number, it's easy to say, okay, if I have 100 meters, what is it going to be? Just multiply by 100, right? So it's very easy to work with dB like that, no matter what the length of the cable is, right? It's dB per meter. So, and of course, you can see obviously why you get more loss for a longer line, right? If the line is 100 times longer, you've got 100 times more attenuation, right? 100 times more attenuation in dB. Okay. So anyway, so I have time to work an example here. Let's see. Just let me see if I have time here. Oh, probably better not. But I'll just say a few comments about it, and then we'll close down here. So now you've got all the background, okay? And now it's time. We'll start this though on Thursday. And I really like this example. It's a really nice practical example that really shows you how to use all of those equations and do it for a really practical example. So on Thursday, we'll start right here. It's a very practical TV coax. Remember, TV coax has a characteristic impedance of 75 ohms. The Z0 is going to be 75 ohms. And I'm giving you a UHF frequency, 500 megahertz. A lot of cable TV operates about that. And we're going to calculate everything about this TV coax, including things like the phase velocity, including the attenuation in dB. So if I take this TV coax and I run it for the TV, the antenna on your house down to your TV set and say it's 20 meters long, how much dB am I going to lose, right? We can calculate all that kind of practical stuff by using all those equations we just went through, okay? So a very nice example if you want to read ahead. So we'll pick back up right here on Thursday, all right? Okay, thank you.